Okay, so now that we have standard ways of expressing circuits in SOP, POS, and we know how to go from words to truth tables to expressions to circuits, let's talk about how we can optimize or minimize these circuits. But first, let's say what is a minimal circuit? What makes a circuit minimal? So say, for example, I have these four circuits. Which of these would I consider the most minimal? Well, first thing I can identify and say, I would like to have less gates, right? So these two at the top have only 3 gates versus the two at the bottom that have 4 gates. So these probably aren't minimal. Now if I compare these two, they both have the same number of gates, but now let's look at the inputs per gate. So this guy has 5 inputs in one AND gate versus 4 in this one. So there's one less input in this first row of gates here. So I'm going to go ahead and say this is my winner. This is the minimal. And so our definition of minimal is an SOP or POS expression. So an SOP expression is minimal if, number one, it has a minimum number of product terms, i.e. the min number of AND gates, or OR gates if it's POS, and number two, among expressions with a minimum number of terms, it has the fewest literals, i.e. the fewest number of inputs to the AND or OR gates. So K-maps or Karnaugh maps are simply an alternative representation of a function or a truth table. So rather than writing a truth table, we can write a K-map, and this will help us to minimize a function. So K-maps list cells in gray code order. So you can see here going from 0, 1, 3, and then 2. The key idea here being that each cell or each adjacent cell differs in only 1 bit. And this is what's going to allow us to then combine multiple product terms together to simplify or minimize the corresponding function. So each loop that we draw, or rectangle or cube, depending on how we draw them, are going to correspond to product terms. So these are examples of a K-map for a 2-variable function, which in itself maybe is not that interesting, a 3-variable function, shown here in the middle, and then a 4-variable function on the right. Notice that each of the cells in each of these boxes are going to differ in only one of the input bits. So for example, going from this cell 0, 0, 0 to this one 0, 0, 1, only the bit or input z changes from 0 to 1. Each cell corresponds to one of our min terms. We're talking about SOPs, so I have M0, and for the 3-variable function, M0, M1, M3, when the input is 0, 1, 1, remember the order of the bits are in gray code order, differing in only 1 bit, and then 0, 1, 0, M2, minterm 2, minterm 4, minterm 5, minterm 7, 1, 1, 1, and then minterm 6. Now for K-maps, we'll probably only use K-maps for a small number of input variables, maybe up to 5 or 6 variables. But K-maps are not only fun, but they give some insight into how computer-aided design tools and synthesis tools such as Avado actually are doing or optimizing or minimizing functions. So let's talk some more about K-maps and how we're going to use them. Okay, so say I have the example function in K-map drawn out. Now for K-maps, there are only certain types of loops that I can draw, certain sizes that are valid, and that are 1 by 1. So essentially, the loops have to have sizes with powers of 2 in them. 1 by 2, 2 by 1, 1 by 4, 2 by 2, 4 by 4, 4 by 2, etc. Now each loop corresponds to a product term, and we also call this an implicant of the function. So for example, all circling each one of these minterms would be valid implicants. And some of the bigger loops as well. So this 2 by 1 by 2 or this 2 by 2. So a product term is an implicant of a function if the function has the value 1 for all minterms of the product term. In other words, all legal loops. Now an implicant is considered a prime implicant if it's not contained within a larger implicant, or in other words, all the biggest loops. So for my example K-map, I have this prime implicant, a 2 by 2. This 2 by 1 is a prime implicant. This 2 by 1 is a prime implicant. This 2 by 1 and this 2 by 1. And the expressions for these, to read these off, so this 2 by 2 is the product term when W is 0 and Y is 0. This 2 by 1 it occurs when X is 1. W is changing, but X is constant is 1 and Y and Z is 0, 1. This 1 by 2 is when WX is both 1 and Z is 1. This one is WXY, and then this final 2 by 1 is when W is 1, Y is 1, and Z is 0. So there's 5 total prime implicants for this example. Now, if a minterm is included in only one prime implicant, then we say that that prime implicant is an essential prime implicant. And for our particular example, we can identify one essential prime implicant is in the 2 by 2. If I look at this particular minterm, and I usually put a dot to remind myself why a particular prime implicant is essential. So this 2 by 2 is an essential prime implicant. For these minterms, there's multiple options, but for the bottom right corner here, and minterm 10, I can see that this 2 by 1 loop is also an essential prime implicant. So if I wanted to derive a minimum SOP expression for this function, I'm first going to select the 2 essential prime implicants. I have no choice for those. So I'll have the 2 by 2, W and Y naught. And then I'll select the other essential prime implicant, this 2 by 1, which is W, Y, Z naught. And then I'm going to choose the fewest amount of other prime implicants to represent the rest of the function. So these are my 2 essentials, and the remaining prime implicant to cover everything else is this one right here in the middle to get the last 2 ones, which is WXZ. And so this is my min SOP expression. So to summarize, so a minimum SOP expression is a sum of prime implicants. Specifically, it's going to consist of, number 1, all the essential prime implicants, and then as few other prime implicants as possible. So the procedure for using a K-map is to first find all the essential prime implicants. In other words, if you can find a 1 in the K-map that's only covered by 1 prime implicant, in other words, there's no choice on how you can circle that one, then yes, that prime implicant is essential, and you have to include that term in the min SOP representation. So a little tip here, always look on all the sides of a 1, and as you find each essential prime implicant, draw its loop. And then number 2, cover the remaining ones using as few prime implicants as possible. And here you want to look carefully. Can you cover all the ones with 1 loop? What about with 2 loops or with 3 loops? So always try to cover with the fewest amount of additional loops. Also be careful because loops can wrap around the edges from left to right or from top to bottom with K-maps.